last time I introduced the Verma module, which was defined like this. G is my complexification of my enveloping, complexification of the Lie algebra, and UGC, the enveloping algebra. We had the decomposition of G as n minus plus Tc plus n plus. Then one considers the I don't remember if I use this notation. Anyway, I now use it. Now let lambda be a linear form on Tc to C. Then one looks at the following. Let I lambda be the left ideal generated by H minus lambda H GTC and n plus n plus. Then V lambda, I don't know if I use the same notation, but anyway, V lambda will be the space UG by I lambda. This is a module corresponding to lambda. And we saw last time there is the sum of all proper submodules of V lambda is a proper submodule and is hence the unique maximal submodule. In other words, equivalently, I lambda maximal UG submodule or proper UG submodules equivalently I lambda is contained in a unique maximal left ideal I tilde lambda, and let me denote last time I don't know if I what notation I used. Did I use this V lambda for the Verma module last time, or did I use it for the irreducible module? Anyway, I mean, let me now shift gears and introduce new notation if you like. So the
This one m lambda and d lambda was what?
UGC by I lambda tilde gives unique irreducible quotient let me call it m lambda, whatever I called it last time, I'll call it m lambda now. Unique irreducible quotient m lambda. So, in other words, we are associated to each lambda in Tc star, the dual we have associated an irreducible G module. Yeah, irreducible G module m lambda. And last time I stated the result which I am yet to prove. It says the following: m lambda is finite dimensional if and only if 2 lambda alpha by alpha alpha g for every alpha in delta. Oh, sorry, it's in z plus for every alpha in pi. This obviously, we have seen that this is a necessary condition. If you have finite dimensional representation, we have this condition. What I am saying now is it is sufficient to conclude that the thing is irreducible. How does the proof go? Yeah. We will do fix that V lambda in m lambda be the unique eigenvector of H Tc annihilated by n plus and with eigenvalue lambda. We know there is a unique such eigenvector in the work. We know that there is such a unique eigenvector in the Verma module. Therefore, in the quotient you get a unique eigenvector. I mean unique up to scalar, unique non-zero this property. Fix this V lambda. Now let us look at.
Not reduce the problem to SL2.
Sorry?
Unlike many other things, it is not by SL2.
Not quite, but SL2 does play a role. We will use very much representation of SL2 to do this.
So you don't want to independently prove the theorem for SL2.
Sorry?
You don't want independently to prove this theorem for SL2.
In the process, you will be proving for SL2 as well. I mean, basically, the proof does not follow from a proof for SL2, but the method of proof for SL2 generalizes. Okay, what in fact what I want to do is this. Let's fix alpha in pi, simple root, and look at the vectors e minus alpha per r. We know that E alpha of V lambda is 0, and let me denote Vk to be f alpha per minus k, f alpha per k, not E minus alpha per k, V lambda. Vk, we know that HVK equals lambda minus 2k well, I am assuming also that E and we will have the relation H alpha E alpha. As I wrote down E alpha E minus alpha, if you take the inner product to be 1, then the bracket will be some multiple of what I want. So, if you like, maybe I'll write so that there is no confusion about that. E prime alpha, no, I want this condition. No, E alpha earlier didn't satisfy this condition, but I now want this condition. I want the SL2 basis taken over to the 3-dimensional GeoGebra generated by E alpha and E minus alpha. Fix such a thing. Then if you have that, then H minus Vk equal to 2k, because the eigenvalues of H in any finite dimensional representation we know are even integers of this H alpha. So HVk is lambda minus 2k. Now what happens to E minus alpha Vk? I claim this is equal to some constant Ck times E alpha of Vk is Ck Vk minus 1, it's Ck in C, and we will determine the Ck inductively. How will I do that? Observe that. So, if E alpha Vk is Ck, then E alpha of Vk plus 1 by definition E alpha of E minus alpha of Vk, that is the definition of. So, E alpha Vk plus 1 sorry, I am interested in E alpha Vk plus 1, that is equal to E alpha E minus alpha Vk, which equals E alpha. I can now this can be written as H alpha Vk, yeah, so H alpha Vk plus E minus alpha E alpha Vk. E alpha Vk is by Ck of Vk. H alpha Vk we know is lambda minus 2k Vk. Sorry, have I written it right? E alpha E minus alpha is H alpha Vk and E minus alpha Ck, so it should be Vk minus 1. So, it's lambda minus 2 H alpha plus Ck whole thing into Vk. So, you find that this is what has to be Ck plus 1 by induction. This is true. So, you find that you actually get Ck Vk plus 1 Ck plus 1 Vk, where Ck plus 1 is this constant here. So, Ck plus 1 minus Ck you find lambda minus 2
K.
to H alpha,
Lambda
or lambda minus 2 K H alpha. No, sorry, lambda minus 2 K of H alpha, which we know is, sorry, why did I write 2K? H alpha Vk is, I'm sorry, this is simply lambda H alpha. H alpha Vk is lambda H alpha minus 2K plus Ck alpha. So you find this Ck plus lambda H alpha minus 2K. Then let Ck minus 1 minus Ck minus 2 and so on. Add up, you find lambda H alpha. So you find Ck plus 1 equals lambda H alpha. How many terms are there? You go to 1 to K plus 1. So lambda K plus 1 lambda H alpha minus 2 into 1 plus 2 plus 3 plus K, it's going to be K into K plus 1 by 2. Okay. So Ck plus 1 you find is K plus 1 into lambda H alpha minus K. Now lambda H alpha is a positive integer, so it vanishes for some K. At some point, some K, lambda H alpha equals K. So you find that Ck plus 1 is 0 if K equals lambda H alpha. Ck plus 1 is 0 if K equals lambda H alpha. But what is Ck plus 1? This means E alpha Vk plus 1 equals 0, because that's what E alpha Vk is Ck, so E alpha Vk plus 1 is 0 is the conclusion. Now look at Vk plus 1, hence, well, I also want to say that we want to claim that E beta Vk plus 1 is 0 as well for every beta greater than 0. Why is that? No, E beta Vk plus 1 is an eigenvector of the form with eigenvector for H with eigen character or weight equal to beta plus, should say this beta H alpha. So again character beta on Tc I am talking about, beta plus sigma, sorry, lambda minus it went up to K plus Vk plus 1 to K plus 1 alpha. But we know that every eigenvalue in this thing, every eigen character is of the form lambda minus sigma m alpha 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 in pi alpha in, yeah, with m alpha greater than or equal to 0. That is the form. But what is this here? It is from lambda minus 2k plus 1 alpha
Plus beta. There is a beta there. Plus beta.
yeah, the beta itself is a positive thing, so it is going to be plus sigma C alpha alpha with C alpha greater than or equal to 0. Now this, that's what this looks like, but this is we need lambda minus C alpha. There is a C alpha alpha here. Now, but if you look at C alpha, if some simple root other than alpha figures here, that's obviously not possible, because every root there is from lambda minus, this has to be lambda minus sigma some a alpha, a beta, a gamma in pi. Here alpha is in pi. So if there is one beta which is not alpha, if it figures here, then it is not in this form. Coefficient has become positive. So it is ruled out, and we have already seen that if I rule that out, if the root is simply alpha, but that is not possible, because we know that E alpha kills it. So this proves that. So this implies that E beta of my Vk plus 1, E alpha Vk plus 1 is 0, now E beta Vk plus 1 is 0 for every beta in delta. This would mean Un minus Vk plus 1 is a submodule. Is a non-zero. If Vk plus 1 is not 0, Un minus Vk plus 1 is a submodule not equal to m lambda. I called it m lambda or m bracket lambda maybe. Yeah. Un minus Vk plus becomes a non-zero submodule of m lambda, which is not equal to proper submodule, but that is impossible because m lambda is irreducible. I have taken m lambda to be irreducible. Implies that Vk plus 1 is 0. That proves that E minus alpha over k plus 1 E minus alpha, yeah, k plus 1 V lambda is 0. I mean, if that is non-zero, you arrive at a contradiction. Okay. Entirely, this is for a simple root, that k will depend on, k is actually equal to 2 lambda alpha by, which let me call it k alpha. So you have this for, this is true. I argued it is one simple root, it is going to be true for every simple root. Implies this holds for every simple root. Now, I want to say that this implies Un minus, sorry, let me write x power, let me E alpha 1 power R1 E alpha 2 power R2 E alpha q power r q, b is 0, b lambda is 0 if r1 plus r2 plus rq alpha I in delta plus. If r1 plus r2 plus rq is sufficiently large, the point is that you first of all you can write any of these. No, the point is, let me write E alpha and pi generate un plus as an algebra. Okay. Then, moreover, this is first comment. Secondly, every element, this is u1 minus alpha and pi. Every element of u1 minus is a linear combination of monomials of the form E alpha 1 power p1, E alpha 2 power p2, pq, where alpha 1 and alpha q is a listing of simple roots and it's a ordered listing. It's in that order I am taking the thing, and p1, p2, pq integers. This is clear because we've seen that the Poincare-Birkhoff theorem tells you that the whole thing is the associated grid is a polynomial algebra, which means if I take any element, you take the listing of simple, which means you can write this with, if you take alpha 1, alpha 2, alpha q to be all positive roots. If you take them to be all positive roots, the Poincare theorem tells you that everything is a monomial in that. But now, if I look at, here the listing, I have to be careful here. Let me at this point say linear combination of or listing of simple roots, so listing of positive roots. Positive roots, and take it in this order. So I want to claim that I want to say that if you take a monomial of a sufficiently high degree, it kills the vector v lambda. That's what I want to say here. The point is that you note that if alpha is not simple, I can write alpha as E alpha or E minus alpha as some constant times E beta E gamma, with beta gamma with at least with one of them simple. Gamma simple, and then this is nothing but in the enveloping algebra it is E beta E gamma minus E gamma E beta. That's what it looks like. But then if it occurs at some power, is expanded to get monomials, but not in a specific order. You get things like, so you find that E beta power p E minus beta power p should be E minus beta, E minus gamma, gamma simple. It will be some E minus psi 1 E minus, let me write, no, this, yeah, E minus psi 1 E minus psi power R1 E minus eta power S1 E minus psi power E minus, what did I have there? Beta E minus beta or RQ. It expands out like this. I mean, you have E beta E gamma minus E gamma E beta, E beta E gamma minus E beta gamma. So you can combine this with something here, something here, something here. When I do that, I get an expression like this. So to prove this is to be 0, you just have to show that if you have a monomial of sufficient length, so third statement is if one has a, if let me say E alpha 1 Q1, yeah, QR V lambda 0 if Q1 plus Q2 plus QR is sufficient, where the alpha A are in pi. There can be repetition. So, this again, what you do is, the point is that if you can get all the alphas right up front, if it's a suppose this is very large, I keep switching, then I'll get something else, a bracket plus something, and so on. You will go on like that. And ultimately you will find that you can get, if this occurs with a sufficiently large power, then you can bring it down, and you can come to this, you can get sufficiently high, the k alpha 1th power of this will be 0. If it's, see, the point is that there are only L simple roots. If you have L times yeah, if Q1 plus Q2 plus QR is greater than, I don't know, some, maybe you need something more, it's safe to take L square times max k alpha and pi. If you take that many, if there are that many factors, then at least one of them will occur to the power k alpha. There are only L roots. When you add up, fix an alpha and you add up, at least one of them will come, and try to bring it to the forefront, and when you do that, sometimes you get brackets which will disturb it, but which will mean you get one less. Okay. And when you do that kind of thing, ultimately if you can move everything down here to this end, and then you will get a sufficiently high power of q, high power of alpha 1. Say, let us assume that alpha 1 is the one which occurs in the highest number, and you keep pushing it alpha across like this. The right way to do is to do it by induction, and then you find you can get a sufficiently high power of this here, which we know annihilates V lambda. If it's maximum more than k alpha, you will get that many. So that's essentially the proof. So why that implies that we know that UG, I mean m lambda is UN minus V lambda. We know this is equal to this. The Verma module is true, so for the quotient is true. But look at this. You know that if you take all those monomials with R1 plus R2 plus RQ greater than some fixed number R, or maybe some number which I will call capital R, greater than or equal to R, then what I want to say is this: UN minus V lambda is finite dimensional, because this becomes a quotient of UN minus modulo ideal generated by these monomials with E minus alpha 1 per R1, E minus alpha q per RQ with R1 plus R2 plus RQ. See, the ideal generated by this in the polynomial ring, if you look at the polynomial ring on as many generator on Q generators, then the monomials generated by this form a codimension finite ideal. Now use the Poincare-Birkhoff theorem, it is going to be true for UN plus as well, because essentially associated is polynomial algebra. So whatever you can do for polynomial algebra carries over. That does the job. So, and that is quotient of this, and this is finite dimensional. So m lambda is finite dimensional. We have shown that m lambda is finite dimensional if lambda satisfies that integrality condition. 2 lambda h alpha, 2 lambda alpha by alpha alpha is an integer for every non-negative integer for every alpha, then it is. Now
maybe whatever you did in between was not necessary by appealing to PPW.
sorry.
I mean this complicated step of using non-simple roots in terms of simple roots, this intermediate step
Right.
is not necessary, because you can directly apply PPW on all positive roots, or
PPW.
Poincare-Birkhoff theorem,
Yeah.
on all negative roots,
Right.
and then you will write UN minus.
No, but I have not proved that a sufficiently high power of a positive root kills V lambda. I only proved for simple roots. If I do that kind of thing, keep applying k alpha,
So you,
when I see it doesn't go up, you have to be careful.
you need to prove it for all
If you can prove that it is killed by
negative roots, all powers of negative
some purpose, then you are done. Yes,
then you are done.
then you are done.
But maybe that's a easy and intermediate
That,
step.
no, that maybe the argument I gave works there also, because when I started V lambda, I kept pushing back, and then I land up in that. But then if I use a root beta and push it back, I'll get something like k minus lambda. So sorry, I'll get lambda minus k alpha plus beta. This, well, one doesn't know what it looks like. I mean, it could be, so you may get it cannot involve any root other than alpha. Okay. If it's if beta involves a simple root other sorry beta involves a simple root which is different from this, it comes with a positive sign, but I cannot say, when it will be lambda minus still non-negative linear combination. Maybe the argument can be modified.
And in any case your argument needs to deal with that also.
Right.
And maybe that would be a easier intermediate step, and then the
possible.
step.
It's possible. What Prasad is suggesting is that prove the statement I made for simple roots,
to all roots.
for all positive roots. Okay. Well, yeah, I think it can be done because even if you apply alpha, when I apply, what happens is that it is certainly true that E alpha hold on. Yeah, you have to argue a little more carefully. The point is, I think the argument will work. It's E alpha power k v, okay, some you look at the argument given for the simple root. I got down to saying that I looked at E minus alpha power k. The point is how to argue a little more carefully. The thing is that, no, let me put it like this. In the Verma module situation, you take the un minus v e lambda, which is contained in un minus, this is the SL2, alpha and SL2 plus. It turns out that you have an injective inclusion here. If you use this, then you can conclude that some power of k will annihilate that as well, because when you apply E alpha back again, see this becomes stable under G alpha. This becomes stable under that. Once I know that this sits inside here, the Verma module corresponding to, if in the SL2 you get a Verma module, that's is a submodule of this, stable under SL2, and so if you do that, yes, then it works that E alpha power k vanishes for every simple root, and then again the polynomial, you look at the powers x1 power k, if you have a polynomial algebra, you look at the elements x1 power k, x2 power k, xn power k. If they are all kill some vector, then it's a finite dimensional thing. Yeah, I think that's a simpler argument. But the point is that you have to be careful about what you really need to use is the following fact: un minus ug is a free un minus module.
That's also Poincaré-Markov.
That comes out of Poincaré-Markov. It's a polynomial building in more variables, it automatically comes. So that's what you really need. Anyway, one way or the other, we've now shown that every finite dimensional representation corresponds to a dominant weight, highest weight, with the property that 2 lambda h alpha by alpha alpha is an integer. So there's a complete bijective correspondence between the two. All right, that done. Now,
A priori, there is some issue that these numbers are integers for simple root versus they are integers for all roots.
yeah, once they are integers for simple roots, they are integers for all roots, because we know that the while group acts transitively.
But lambda alpha.
The while group acts transitively on the chambers, which implies any root can be taken into a simple root by element of the while group.
Yeah, but that will also.
No, in any case, sorry.
That will also, so meaning the hypothesis that 2 lambda alpha upon imply it is integral for all roots.
Right.
It may need some argument.
It does need some argument, right?
And
I agree.
that argument is not being used here.
Yeah, you're right. Mm.
I'm sure that is true, but that also needs some argument somewhere.
Hold on, let me see. Yeah, the point is that it's also true that the H alpha are also integral linear combination with positive things, but even that is not enough. You need to know that 2 lambda alpha by alpha is an integer. You have denominator H alpha there.
Yes.
Now let's.
Whereas, yeah.
Hold on, let me think.
No, I think integrality for a simple alpha is enough. Integrality only for simple.
So will imply integrality for any alpha. It's true.
Yes, but
The,
it needs some small.
right. I'm just thinking. What's the argument? I'm just a bit lost now to come. Yeah, that's a point which I should anyway have proved. I may even need it later. So the thing is that 2 lambda alpha by. Anyway, the point is that as far you can, the thing it's a if 2 lambda alpha by alpha is an integer, is true for any finite dimensional representation. We know that for a fact. For every positive root. Now, so make the assumption for every positive root. It is we will not. So the assumption is right. 2 lambda alpha by alpha z for every alpha delta plus. Actually, this is equivalent to. I won't go into this. Maybe I'll prove this a little later, but our assumption now is 2 lambda alpha by alpha is integral and positive for every simple root. Okay. This statement is not proved. That's all. Maybe I'll still prove it sometime, but I plan to give only one more lecture by that time. Let's see. Okay. All right. Now, at this point, now the thing is that I would like to write down. So let me. So lambda is a. Let me denote by xt the group of abelian group of all characters on T. So then we know that if you take rho an irreducible representation of the compact group G, then I know that chi rho T, the character of trace rho T, T in T, sorry, rho G, G in G, it's a class function that is chi rho of G u G inverse is chi u, right, u G equals chi G for every u in G. This means we know that the representation is completely determined if we know chi rho. Now we know that every element in G has a conjugate in T, so it's enough to chi rho is determined by chi rho restricted to T. Oh, this rho is probably bad notation because I want to use rho for something else. Let me write R. R is the representation. Now, so let's fix a R, a finite dimensional representation of the compact group G, and we fix as we have been doing the root system and order and everything on that. Let lambda r be highest weight of R with respect to an order, etc., etc. Then one should be able to say what the character of this representation is, because lambda r uniquely defines a certain representation, and I would like to know the corresponding representation. So, we have a formula. The point is this: let chi r be the character of R. Then the statement I want to make is this: chi r of T equals sigma in the while group lambda r plus rho sigma sigma is in the while group. I will say what epsilon sigma is presently, divided by I have to say what rho is and what epsilon sigma is, etc. This is known as the Weil character formula. So, given the representation, given the highest weight, I am able to write down the character of the representation completely. So, what number of unexplained terms here? First, rho is the unique character such that two rho alpha by alpha alpha equals 1 for every simple root. And what is, if you have sigma in W, epsilon sigma is the signature of sigma. The point is this: we know that the Weil group W acts on the torus and therefore in its Lie algebra on Tc. In fact, it operates on T itself and hence on It, which we have been calling HR. And we know that the Weil group epsilon sigma by definition is determinant at W on T. That is the signature of sigma. The point is this: if you take alpha is a element in delta, we know that S alpha, the reflection we have an element S alpha in W, which such that add S alpha is the reflection in some hyperplane, and therefore its determinant is -1 because it operates as -1 on the orthogonal complement of the hyperplane and 1 on the hyperplane. So, determinant, so epsilon S alpha equals plus minus equals -1, and we know that the while group is generated by these reflections. So, determinant of any element is going to be either plus or -1. For the reflections it is -1, but if you take product of two reflections it becomes 1 for instance. So, it is I call it signature in keeping with in the case of SLN what you get is the permutation group on n symbols operating on n minus 1 dimension on n dimensional vector space, acting n minus 1 dimensional vector space, and then you find it what it does is the determinant turns out to be this one. See, on the Lie algebra, if you take SLN, it is contained in GLN, and you take the maximal torus in GLN, the normalizer of the maximal torus in GLN is same as normalizer of the smaller torus in SLN, and then the elements S alpha, when you look at it on the bigger torus, they actually act as permutations on the Lie algebra, and therefore the signature will be +1. But what you are throwing out a one dimensional space in which it operates trivially. So, the determinant remains the same whether you take the coordinates in one space or the whole space. So, and in other words that's the reason I call it signature. It's essentially signature of the permutation in the case of the group GLN. Okay. So, lambda r plus rho, that is a character, I am writing it additively. So, strictly speaking T goes to lambda r T times rho T will be the. So, I look at this, apply the permutation on this element, apply the while group element on this element, I get a new element, multiply by epsilon sigma T, and then chi r T is by definition is going to be this ratio. There is a small problem here in the sense that this thing can vanish at certain points T, but it turns out this does not vanish. This is a chi r T is a, I mean the denominator here vanishes, but chi r T is a good function on it's a character, it's a good function on T. It's a quotient of this, so this means this is going to divide that. This function is going to divide that. In fact, so the number of things I will have to say. Let me denote by C of T will be the algebra generated by this algebra is it's essentially same thing as it's the group algebra of xt. It's a bit, when I say it's group algebra, the multiplication, the next t is written multiplicatively. So that's the multiplication in the group algebra. So CT is the group algebra of this. And an element, okay, f in C, they are all functions on the torus. F in CT is symmetric for the while group if sigma f t goes for every t and t, and I will say it is antisymmetric if sigma f t equals epsilon sigma f sigma inverse t. Notice that the function chi r t is necessarily symmetric. It is the character of the group restricted to the torus, character of the representation restricted to the torus, and since the character is inner conjugation invariant, it is invariant under the inner conjugation with Y group on torus, therefore it is symmetric in our sense. So this is symmetric. This, as you can see, is antisymmetric. If you apply tau to this, you are going to get tau. As sigma varies over W, tau sigma also varies over W, but then you got an epsilon tau which pulls out, epsilon tau, epsilon sigma, etc. So this is antisymmetric, this is also antisymmetric. So the ratio is symmetric. Therefore, it's, I mean, that's one necessary condition if these two sides are equal. If the two sides are equal, so let me denote by ST symmetric elements in CT, and AT will be the antisymmetric elements in CT. Consider now the map CT to CT given by multiplication by, oh, I have to give that a name, multiplication by A rho. Let me first define A from CT to CT. I define this by A of any function f equals T sigma epsilon sigma f of sigma inverse clearly what A, or maybe I should give it call it slightly differently, otherwise. Okay, let me make it script A. Notice that AFC, notice that this is always alternating. If f is any function, I am applying this. If I apply sigma to AF, that is applying to, say, to tau to AF, that will be same thing as tau applied to this. So I get epsilon sigma f tau inverse will get in there. So f of tau inverse sigma inverse t. And then as tau inverse sigma inverse varies, as sigma varies over W, tau inverse sigma inverse also varies over W, and this epsilon sigma can be replaced by epsilon tau times epsilon to epsilon sigma. So epsilon tau pulls out. So it becomes a, so AF f is actually what I called AT. And every element is in the image. It's a standard way in which if you isolate the component corresponding to one irreducible representation of W, which corresponds to epsilon sigma, then this is the way to do it. You just average it with a suitable factor there. AFT equals this, and AF is in AT, and similarly, let me write SF T to be the average. Oh, I have to put in 1 over order W. Epsilon sigma, sigma and W, no epsilon sigma now, simply F sigma inverse T. Then you find that SF is in what I called ST. Lemma, which is easy to prove. AF A respectively S is a W invariant projection of CT on AT respectively ST. This is standard thing in coming from group theory. The way you, it so happens that you have two one-dimensional representations, and for that you can simply write it like this. Epsilon sigma is a one-dimensional representation, and the other representation is a trivial representation. So, it project this AT is precisely, I think I wrote it down. AT is the antisymmetric elements in CT. That the images in AT is clear, AF is in AT, SF is in, I want to say it's surjective. It's surjective is also clear because you take an element of AT and do this averaging on it. What happens? You take an element of AT, if you take average this, epsilon sigma F is already satisfies F sigma inverse T is epsilon sigma T. So, if I multiply with epsilon sigma, this disappears. So, I get back FT. It's FT all the time. Epsilon sigma F sigma inverse T equals F because F is in AT. And how many terms are there? There are as many terms as there are W, and I have divided by 1 over W. So, that is the projection, and entirely analogously for symmetric things. Averaging is a procedure you adopt. So, that is the proof. I am not going to say more about it. More delicate is the following fact. Now, let me, for that I have to introduce the following. Let rho be the character satisfying 2 rho alpha 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 equal to 1 for every simple alpha. Then the map F to F times a rho is an isomorphism of AT on sorry of ST on AT. See, F is a symmetric element, and A rho is a antisymmetric element. The product is antisymmetric. So, this is a map which takes S into antisymmetric elements, and it is clear that it is an injective map, that is easy to see. But these are all I am looking at, these are all analytic functions on the torus. So, analytic function of the torus is an integral domain. So, from that it is clear that this mapping is injective. The point is it maps into AT, the point is it maps onto AT, which is why in the Weil character formula we could divide the numerator by the denominator. The numerator was some alternating function, but any alternating function can be divided by this because of this lemma. This is proved by an induction. Induction on what? See, any alternating element, if phi is in AT, phi is a linear combination of A, C lambda, A lambda, lambda. See, if phi is in AT, we know that phi can be written as sigma phi equals epsilon sigma phi, sigma and W 1 over mod, write phi like this. But phi itself can be written as a linear combination C lambda, where lambda are characters in xt. So, plug it in, so you find, so the conclusion is every element of AT is of the form sum B lambda A lambda with lambda in xt, B lambda in C. Actually, I can notice that A lambda is same as A sigma lambda for every sigma in W. Now, if I look at any lambda in xt, there exists sigma in W such that sigma lambda is dominant, that is sigma lambda alpha actually okay, alpha, well, right, such that sigma lambda alpha is always positive, so it is enough to see, okay, this is integral. Why is that? I take the reason for this is the following. If I choose sigma such that sigma lambda is greater than for every tau in W. It is totally ordered, so I can certainly find one element which is highest among them. Then if you look at lambda, sigma lambda, let me call this mu, then I know that S alpha mu for any alpha in delta in pi, S alpha mu we know is less than or equal to mu. This means S alpha mu is what? Mu minus 2 mu alpha by alpha alpha. This is times alpha. This is what S alpha mu is. And S alpha mu is less than to mu, that means this 2 mu alpha by alpha alpha has to be integral, has to be positive. It is an integer, has to be greater than or equal to 0. If this is negative, then you will get mu plus alpha, which is larger than mu, but mu is the highest. I am adding to mu some positive multiple of alpha, which is the positive root, which is a simple root. So, okay. Okay. So, that shows there is a unique sigma lambda. So, we can actually assume, when I write it like this, I can collect together all those lambdas in the same while group orbit, choose the dominant one among them, and replace that by dominant, because this averaging will give you the same element. So, B lambda A lambda can assume that B lambda and C lambda dominant, that is dominant means 2 lambda alpha by alpha alpha. By the way, for a finite dimensional representation, we know that 2 lambda alpha by alpha alpha is always integer. If I know for simple roots 2 lambda alpha is greater than 0 for every alpha and pi, then it is true the same inequality holds for any other root, any positive root, because any positive root is written as C alpha alpha, alpha and pi, and C alpha greater than or equal to 0. And if I take the, so this is any root beta, beta greater than 0 implies beta is this form, and then 2 lambda beta we know is 2 lambda beta is 2 lambda beta is 2 sigma C alpha lambda alpha, alpha and pi. C alpha are positive, non-negative, and lambda alpha is non-negative, so this is also greater than or equal to 0. So, in general, the earlier proof in the Verma module, if lambda says that 2 lambda alpha by alpha alpha is positive, is a non-negative integer for every simple root, it will follow that 2 lambda alpha by alpha alpha is actually positive for every simple root. It is only the question of dividing by alpha alpha gives you a okay. Now, what, how, so this is, every element is this quant. So, what we will do is the following, we will prove this theorem, we want to prove its rationale, that is, we want to prove it's surjective, because injectivity is clear. The point about surjectivity is done as follows, one does it by, so it suffices to show that for every dominant lambda, there exists symmetric F such that F times A rho equals A lambda. It's enough to prove that statement. Well, I will prove this by induction on lambda. On the, lambda is all totally ordered. So, I will suppose proof is by induction. Well, I don't think I am coming to the end of time. I don't think I will have time to prove it. I will leave it for the next lecture, which means I will probably have to give 2 more lectures, not 1. Okay. I don't think I will finish the wild character formula in 1 more lecture, because it takes a little more work. And then I also want to talk about the dimension formula. The dimension formula is simply the evaluation of the character chi rho at 1, but my character is defined as 2 ratios, both numerator and denominator will vanish at t equal to 0. The trace of the chi of 1, which is identity, will give you the dimension. But if I calculate the trace type with a 0 by 0 situation, so what you have to do is to apply L'Hopital rule. And you have to take partial, it's a partial situation. So several variable situations, you take partial derivatives with a number of times, just not once. With respect to every root, you take partial derivatives, and then it works out right. But working that out takes a little work. So anyway, next time I'll prove the wild character formula. First, this lemma, and once this lemma is proved, I can prove the wild character formula. See. Again, the wild character formula is also proved by induction. Notice that when the take the 0 character, the formula gives you the function 1, because numerator and denominator are the same, lambda plus rho divided by rho, alternatized. So it gives you 1, and that is for the trivial character. Then you will prove it for every, you want to prove it for every dominant character, the same formula, you do it by induction. So up to a point, if you have proved, at the next stage you have to prove that it's the function you get is orthogonal to all the earlier characters and does not involve higher dimensional things, because if you take the anyway, so that's the kind of thing that, okay, I'll stop here, right.